All right, since we're looking at multiples here for this bell work, then we're just listing multiples of 8, so that'd be like 8. That's the first multiple. 8 times 1, 8 times 2 is 16. 8 times 3 is 24. 8 times 4 is 32. And then 8 times 5 is 40. Okay, so 40 would be the fifth multiple of 8. Here's 3 objectives for the day. I can determine the lowest common multiple of values. Then I can simplify fractions, and also I can find missing values of equivalent fractions. Take 1 minute, copy those down. All right, everything that we're going to go over today we've already done, but it's a nice review to get us set up to get started in Unit 3, okay? Because we're going to be dealing a lot with fractions. In fact, pretty much the whole objective for Unit 3 is to learn how to operate with fractions. And, well, I think we may see some operations with decimals, but mostly fractions. And so you can see we need to be able to simplify fractions and find equivalent fractions, missing values in equivalent fractions, which we've done before. And then also I can determine the lowest common multiple of values. This will come into play later, but right now we just need to be able to do that. In fact, even the lowest common multiple isn't so crucial later, but on the homework, if I remember right, they just want the lowest common multiple. So multiples are just where you take the product of a number and a natural or counting number. That's it, okay? So if you looked at multiples of 4, for example, 4 by itself would be 4 times 1. So that's the number, and you multiply it by a counting number. 4 times 1 is 4. 8 would be the second multiple of 4 because it's 4 times 2. Or 4 times 3 is 12, or 4 times 4 is 16, and you could continue this, but the idea hopefully by now is that you have the multiplication tables memorized, because it will be very crucial when we start working with fractions. And that may sound weird, but you'll have to have that down before you start working. Now, do you have to memorize it? Not necessarily, but a lot of these problems are going to take longer, and it's going to be a lot more difficult to understand unless you have that multiplication table memorized. And part of remembering what multiplication is, remember you could also do it this way, which we kind of had seen, right? 4 plus 4 is 8. 8 plus 4 would be 12. And then you could say, well, 12 plus 4 is 16. Okay, same idea there. So you can use addition to kind of make your own multiplication table like this. Generally speaking, we shouldn't have to do that with any values with 12 and lower, up to 12. But once we get to 13 or beyond, then we kind of have to make our own multiplication table like this, which we will see and have seen already. So this is the first 9 multiples of 7, no problem. So, of course, 7 by itself is its own first multiple. If you add 7 to that, you'd get 14. If you add 7 to that, you'd get 21. Now, you could say multiples as well, right? So 21 would be 7 times 3. 7 times 4 is 28. 7 times 5 is 35. 7 times 6 is 42. 7 times 7 is 49. And 7 times 8 is 56. 7 times 9 is 63. And then 7 times 10 would be 70. I guess I went a little bit further there than it asked, but that's okay. And remember, you could use addition, right? You could say, well, 7 plus 7 is 14. 14 plus 7 is 21. 21 plus 7 is 28. 28 plus 7 is 35. 35 plus 7 is 42. And if I remember right, when we did this, by the way, in class, that was for long division, right? When we make our own multiplication table like this. And we showed it different. We did stacked addition, which I think we'll see on the next problem. But again, however you do it, whether you do multiplication or you just start adding with the 7s like this, it's all good because you'll get the correct answers either way. Okay? It's like this one. List the first 4 multiples of 13. Now, of course, you'd always just start with the first value by itself, which is, again, I'm just matching that 13 right there. And then this is the way that we showed it when we started using long division, right? We said, well, let's make our own table. So that means I'd have to add another 13 right there. So in the ones place value, 3 plus 3 is 6. In the tens place value, 1 plus 1 is 2. So that's 26. That's the second multiple of 13. And then to find the third multiple, well, you just add another 13 here. And that will tell you the third multiple. In the ones place value, 6 plus 3 is 9. In the tens place value, 2 plus 1 is 3. So 39 is the third multiple of 13. We only need one more to finish off this question, but just add another 13 to that. So in the ones place value, 9 plus 3 is 12. then carry the 1 over here. So 1 plus 3 plus 1 would be 5, 52. Okay, so I'll highlight these to emphasize them. A 13 is its own first multiple. 26 is the second multiple. 39 is the third multiple. 52 is the fourth multiple. Okay. So usually, and this is pretty normal, where some students are like, look, I want the second multiple of 13. So some students will do 13 times 2. 3 times 2 is 6. 2 times 1 is 2, 26. Yeah, we get the same answer. So you can stack and multiply if you'd like, but I think the addition is a little faster for me. All right, common factors. And when we see the word factors, it's important to remember that factors indicate that we're using some kind of form of multiplication. So, for example, if you looked at factors of 15, and I think we've seen it this way, that'd be like 3 times 5, right? 3 and 5 are factors of 15. You could even extend that and say, well, 1 and 15 are as well. Yeah, sure. Because 1 times 15 would give you 15 as well. Okay? So maybe I should put commas between those and not multiplication. There we go. So 1, 3, 5, and 15 are all considered factors of 15. So if we looked at another number, let's say like 20, right? So you could say, well, 20 could split up into, of course, 1 and 20. But also you could say 2 and 10. And then also 4 and 5, okay? So you can do it this way, and then you could say, well, see how 5 is a common factor between the two? So that would mean that between these two numbers, 5 would be the common factor. Now, common multiples is kind of the same thing. It's just you got to actually list the multiples. There's a different method, but right now we're just going to look at listing the multiples. A number that is multiplied is the multiple of many numbers. So you're looking at different values, and then you're going to make lists of multiples, and then when you see matches, those are considered common multiples. So like these two right here, you got 15 and 3, right? So I'm gonna take 15 here, and I'm going to list multiples of 15. Now I don't know all the multiples of 15 by heart, and so we have to use some addition here to figure out the second multiple and third multiple. Okay. So I'd say let's go and add 15 here. And then that means the second multiple, 5 plus 5 is 10. Carry the 1. 1 plus 1 plus 1 is 3. 30 is the second multiple of 15. And then you can add another 15 there to find the third multiple. And I know some of you know that I've gone too far, and that's okay if you do. In the ones place value, 0 plus 5 is 5. In the tens place value, 3 plus 1 is 4. I'll do one more. So let's go and add, let's find the fourth multiple of 15. So add another 15 here. In the ones place value, 5 plus 5 is 10. Carry the 1. 1 plus 4 plus 1 is 5. Okay. So I have my first 4 multiples in red here of 15. But then I will list multiples of 3. And I guess I'll do that in green here. Now I'm not going to use addition for this because we should have at least the first 10 multiples of 3 memorized. So here we go. 3. I'll do that a little bit bigger, but 3. And then 6, 9, 12, 15, 18, 21, 24, 27, and I'll stop at 30, okay? So you can go further if you'd like to, but I'm going to stop there. Now we see, just with the two lists that we have, that 30 is a common multiple of both. Right here. Now, is it the least common multiple? No, it is not. Because if you look at 15, it's not just the multiple of 15, but 3 as well. And so if we were looking for the least common multiple, it would have to be 15 there. So we'll make this least common multiples. Okay, so again, we're kind of looking for the matches when we do this, but not just matches, because we can see that there's going to be a lot of matches if you continue the list long enough. But when I ask for the least one, it has to be the lowest of all of the common or the matches. Find the least common multiple of 4 and 7. So again, hopefully there's no need for addition here. We should have at least the first 10 multiples of each memorized. And I think we did 7 already, so I'll do 7 in purple here. 7, 14, 21, 28, 35, 42, 48, 56, 63, and I'll go to 70. Well, what about 4? Well, that'd be 4, 8, 12, 16, 20, 24, 28. And by the way, some of you may even stop there, which would be fine. I'm just going to continue because, I don't know, it's so much fun. So, right here, do we see any matches between these multiples? Now, if I didn't see any matches, then I'd have to actually continue this further. But I don't see any. Well, I do see any. I apologize. I do see some. But if I didn't, then I would continue. I see a 28 right there. In fact, that's the only one that I see in the first 10 multiples of each. Of course, 28 is a smaller multiple of 7 because it's a bigger number. But yeah, that right there is the lowest common multiple, LCM, of 4 and 7. Sometimes, and this usually happens, students will say, well, what about 0? Well, we don't usually include 0 as a multiple when we're looking at numbers like this. Otherwise, it would just always be the lowest common multiple. And again, do you always need the lowest common multiple in the future? No, you do not, but sometimes it comes in pretty handy. Quick review on proper and improper fractions. Remember that proper fractions have denominators that are bigger than numerators, and improper fractions have numerators that are bigger than denominators, which means that if you have an improper fraction, you could change it into a mixed number. We're not going to be doing that because when we're in a pure mathematics situation like we are, improper fractions are easier to use with calculations. So again, it's important to know the difference because we're going to be using this vocabulary quite often, which we already have in the previous unit as well. So right here, let's go ahead and write this situation as this will be an improper fraction. And it tells us it's an improper fraction. How do we know? Because we have a whole piece and then some left over, right? Which means that since it's an improper fraction, the numerator will automatically be bigger than the denominator. The numerator tells us how many pieces are shaded blue. The denominator tells us the sizes of the pieces or how many pieces will make a whole. I'll call this pizza, but whatever. So for me, I'm going to start with the numerator. So I'm going to count how many blue pieces there are. 1, 2, 3, 4, 5, 6, 7. So I have 7 blue pieces. So that is my numerator. Well, what are the sizes of the pieces? Well, if I look at this whole piece right here, I can see that there are 6 parts that make that whole, which means they are 6th size pieces. And so this fraction, 7/6, represents the area that is shaded blue. Could you write this as 1 1/6? Yes, you could. But really, in this unit, we're focusing on improper fractions and not mixed numbers. What about simplifying fractions into lowest terms? Well, if you ever see any form of simplification of fractions, that means that you're going to need to use division. Okay? We always use division to simplify fractions. Now, when we say we're going to use division, you'll need to remember that when you use division, you have to use the same division on the numerator and denominator, okay? So if you look at a fraction, and it doesn't really matter what the values are, so I'm just going to put a couple boxes right here. Doesn't matter what those numbers are. If you, for example, if you were to perhaps divide the denominator by 8, then you'd have to divide the numerator also by 8 in order to make it simplified. Doing this means that you're maintaining the value of the fraction, but you're showing it in a different way. That's what this is saying. You have to be able to show fractions in different ways, but not change the value. After you do that, then it's very easy to start operating with fractions, which is what this entire unit is all about. And that would be considered simplifying fractions. Now, when we simplify fractions like this, it's also called scaling fractions. Again, scaling fractions means that you can go with multiplication or division in order to change the look of fractions, but you have to use either multiplication or division. Never use addition or subtraction when scaling fractions, all right? So that would be simplification or even expansion of the fraction. So like this one, it says, what fraction of the circle is shaded blue? So just right off the bat, this wants an unsimplified fraction, right? So once again, I just count how many pieces are shaded blue. 1, 2, 3, 4 pieces are shaded blue. That's my numerator. The denominator tells us the sizes of the pieces. So there's 4, 5, 6, 7, and 8 pieces. So the sizes of the pieces are in eighths. So there's 4 pieces shaded blue out of 8 pieces, 4/8. Now, what is a simplified fraction? And I think we've seen this before. You could, if you wanted to fully simplify this, you could say, look, there's this one big piece out of what would be this two pieces right here. So we can also say, look, there's one full piece out of two pieces. They'd be rather large, but that's okay. Some of you may have even seen this just a little bit before, but you can kind of split it this way. And now you've got 1, 2 pieces out of 3, 4 pieces, okay? Now, is 2/4 the most simplified? No, it is not. It is simplified, it's just not most simplified, which is what we would want. And to make it most simplified, we'd have to change it into 1 piece out of 2. Well, how would that work with the fraction that we had before? So if I take the 4/8 right here, what you would have to do to make it fully simplified into 1/2 is you'd have to say, you'd have to divide. Remember, it's always division because we're simplifying here. You'd have to divide these both by, oh, I should say 4 there, because these both are divisible by 4. So 4 divided by 4 is 1, 8 divided by 4 is 2, you get 1/2. Simplifying fractions in the lowest term. So again, you can just look at the numerator and denominator. You may have to ask yourself what both numbers can be simplified by, or are they divisible by the same number? If they're not, then it should be fully simplified. But if they are, then just keep dividing, okay? But again, simplification always means that we're going to be using division on these, all right? Or if it says lowest terms, that indicates division. So even though it's talking about multiplication or division, it's just saying whatever you do to the numerator, you have to do to the denominator, or vice versa. So I like this one, 24 and 32. Now we look at this, yeah, we want it in lowest terms. Some students would say, look at the 4 and 2 in the ones place value. That means that they're both divisible by 2. Now that's true. I'm going to take this just a little bit further, though, and say, look, 24 and 32, they're both divisible by 4 as well. See that? So you can say, look, these are both divisible by 4. But even further, we can divide them by an even bigger number. They're both multiples of 8. So let's go and divide these by 8 instead, and that's about the biggest number I can think of. In the numerator, 24 divided by 8 is 3. In the denominator, 32 divided by 8 is 4, 3/4. Now, we would always check your fractions, even though we divided this by a bigger number. Just check to make sure that 3 and 4, or whatever your numerator and denominator are, cannot be further simplified by any values. And while 3 is divisible by 3 and 1, 4 is not divisible by either one, so that's just complete right there. That is fully simplified as is. All right, now there's a second method. Right here we got what we call prime factorization. This is usually used with larger numbers because it means you don't have to think about what is this divisible by, and it helps you to avoid some long division if you don't know what it's divisible by, okay? So here we go. I'm going to use the second method here. Could you just keep dividing these by 2 or whatever number they're divisible by? Yes, you could. But I'm going to use prime factorization on this. All right, so we're going to divide these into lowest terms, meaning I'm going to get a fraction, but I'm going to find all of the factors, the prime factors of both. So what can I multiply? I'll start with the numerator there, 54. What can I multiply? What two numbers can I multiply to get 54? I would say probably 9 and 6 on this. And then I would know that 9 splits up into 3 and 3. These are prime numbers. And then 6 splits up into 3 and 2. So those are prime as well. Okay, so instead of writing 54 as 54, I'm going to write it as a product of its prime factors, which I just found in red there, which is 3 times 3 times 3 times 2. This is still 54. It's just written in a different way. That's all. It's written in a way that I want it. Can't we do the same with 144? Yes, we can. And 44, if you have your multiplication tables memorized, you'll see it's one of those products on the multiplication table with 12 and 12. Now 12 is not prime, which means we can further split these up. I would probably say 4 and 3. Right there, you could say 6 and 2 if you'd like, but 3 is prime, so I circle it. 4 splits up into 2 and 2, and so they're prime. Well, what would have happened if I did 6 and 2 there? Well, the 2 would have been circled, and then 6 would have been 3 and 2. Okay. So 144, I'm going to list these from left to right here. So that would be 2 times 2 times 3 times 3 times 2 times 2. Okay. Meaning if you multiplied all 6 of these numbers, you would always get 144. So again, I have the same value, 144. I'm just showing it different. And now it's time for the simplification process, which means if I see any matches in the numerators and denominators, I can make it a phantom 1. There's a 1 right there. There's another one. There's another one right there. Now in the numerator, I have that red 3 left over, and in the denominator, I have 1, 2, 3 2's left over. They're all factors, which means they're multiplication. What would this be as a simplified fraction then? The numerator is just 3, but in the denominator, 2 times 2 times 2 is 8. And this would be considered fully simplified using the prime factorization method. Now again, Kitty just said 54 divided by 2 is 27, and 144 divided by 2 is 72. Yeah, and then you could keep dividing by 2, and then 3, and then whatever the heck else you got to divide by. Okay, but ultimately, we'll always simplify into 3/8 one way or the other. Fractions like that, but now we got to be able to change fractions into new values, into equivalent values, but again, they're going to be equivalent, so we're going to change the way the fraction looks, but not change the overall value of the fraction. So it kind of works like this. Remember, you can only use multiplication or division when changing the look of a fraction and then maintaining its value as well. So on this one, if I were to look at this example right here, it says just write an equivalent fraction to 7/8 right there. So a lot of students say, look, I'm just going to scale this up by 2, and that's kind of an easy way for us to do it. 7 times 2 is 14, and then 8 times 2 is 16 like that, right? I personally kind of prefer to just say, look, let's take the 7/8. If I multiply those both by 10, it's just kind of like tacking a 0 onto the end. So I'd end up with like 70/80ths. Again, it just said find an equivalent fraction. It didn't say any specific fraction, just an equivalent fraction right there. So those are equivalent. Of course, there's lots of other ones that you could have chose as well, such as, let's say 21 24ths. Multiply them by 4, you would have gotten 28 32nds. Multiply them both by 5, 35 40ths. Yep. So all these that I've written right there are considered equivalent. They're the same value, they're just written differently, that's all. All right, so on this one, we got to find an equivalent fraction to 1/6, but this one is forcing us to find it with a specific denominator right there. And the denominator right now is 42. So that means I'd have to look at this and say, I'm going to take this, let's make this bigger. I know that I'd have to go from 6 to 42 right here. I'd have to multiply 6 by something to get 42. Now that means I got to multiply the 1 by the same factor in order to make this x. Now in the past assignments, the x was just kind of an empty spot. Now it's just an x. We just need that value to make it a true statement with the equal sign, okay? So again, if you know your multiplication tables, you know 6 times 7 is 42, which means you'd have to multiply the 1 by 7 to make x 7. And that would be considered the value of x. If you replace x with 7, you'll get a true statement with this equal sign. 1/6 is the same as 7/42. All right, in a problem like this one, same idea. Once again, what do you have to multiply 4 by to get 24? That is the same factor that you will multiply 1 by to get x. And we know that 4 times 6 is 24, so 1 times 6 would give you the x value, which is then 6. 1 times 6 is 6. So if you replace that x with 6, you get a true statement. All right, here we got 3/5 equals 18 over x. So we got to figure out the denominator on this one. Take 1 minute and try this one out. All right, I'm going to go and do this one. If you're still working, finish up and then check your work with what we get, okay? So on this one, let's see. All right, so on this one, I see that I'd be like going from 3 to 18 right here. 3 times what is 18? I'd multiply the 5 by the same value to get the x. So 3 times, I know 6 would be 18. So I'd have to do 5 times 6 to give me x equals 30 like this. So that means x would be 30. If I replaced x with 30 here, I would get a true statement, okay? Now you can see all of these ones that we've just barely done. That's going from something small like 3 to something big, and that requires multiplication. If we have to make something smaller, like if you go from 18 to 3, then you'd know you'd need to use division, okay? All right, so on this one, we see the x is on the left side, and that's okay. But again, the main idea is that we're taking something big and making it smaller, right? So if we looked at this problem here, we want it to be an equivalent fraction, but we got to make this denominator a specific value, right? So what would we have to do to 10 in order to make it a 2? Since it's making the 10 smaller here, you'd have to divide it. So what would we have to divide it by? You'd have to divide it by 5, and that would give you the 2, right? So we'll have to divide the 55 by the same value, 5, and then that would give us its corresponding x value there. And if we do that, 55 divided by 5, that would be 11, okay? So if you replaced x with 11 here, you'd get a true statement. Now you'll notice with some of these problems as well, if you replaced x with 11, this one's simplified, but not all of them are. It doesn't matter if they're simplified, because in the future we may want them to be unsimplified, but we need the denominator to be a very specific value. What about problems like this one? Again, we're going to write the equivalent fraction, but some students say 3 is not a fraction. It is a fraction, you just can't see the fractional part. It's always over 1, okay? So right here I can see that I'd have to multiply 1 by something to get 12, so 3 times the same something would be x. And that would be 1 times, well, 12. So 3 times 12, yeah, thank you. 3 times 12, that's 36 instead. There we go, now I got it right. All right, quick review on adding with same signs, because we're going to see addition and subtraction of fractions. Sometimes they're positives, sometimes they're negatives. Just remember, a negative added to a negative just makes the answer more negative, which is why we end up using addition anyways. Remember as well, if you have an addition sign, there's no need for keep, change, change. We want addition. We only have addition when we operate with numbers. So like this one, right? Especially with negative numbers. So this one's -7 plus -6. I know if I take a negative and add something that's negative, I'll get something just more negative. And that's why we take, since it's more negative, you just take the two numbers and add them together. 7 plus 6. This will tell me how negative it is, and that'd be 13. So the final answer here is just -13. Boom. Now again, we've seen all this stuff. We should be able to do this stuff, but we have to be able to do it with fractions, and so it's important that we get this integer stuff down, which we've seen before. What about if the signs are opposites? If they're opposites, but again, if it's addition, there's no need for keep, change, change. If they're opposites, then you look at which one there's more of. Is there more positives? Is there more negatives? That will be the sign of the answer. And then, since they're opposites, they're going to zero each other out or cancel each other out. And so you got to actually take the big number and subtract the small number, okay? And then, of course, keep your predetermined sign, because you know if there's more positives or negatives in the beginning. It's like this one. We look at -18 plus 25. I know that there's more positives here than there are negatives, which means that my final answer should be a positive, right? So how positive will it be? Well, take your 25 and then subtract the 18 negatives, because they're going to zero out those 25, and that will tell you how positive it will be. Change the 15, 5 to 15. 15 minus 8 is 7. 1 minus 1 is 0. So that'd be +7 there. And that'd be considered the final answer. We don't need the positive sign either. What about subtraction as addition? Well, remember, if you ever see subtraction, we change it into addition with keep, change, change. We only add with negatives. We never actually subtract with them, okay? And we do that by changing the operation to addition with keep, change, change, which we've been doing, which we've seen, and which hopefully we're used to. And remember, the change part, that's the part that we see where we just put in a couple marks into the problem and then we're done. Or we can operate. So something like this, I got -8 minus 8. And so on this one, I'd say keep the first 8 negative, change the operation into addition, and then this second 8 goes from positive to negative, okay? Now I'm adding a negative to a negative, which means the answer will just be more negatives. So there's my negative sign. Take the two values, 8 and 8, and add them together. That's 16. So how negative is that sum? It's -16. What about a problem like this one? Well, keep, change, change is going to change this. So it's -15 keeps its sign. Then we change it like this. Some of you may even benefit from rewriting it as 15 plus +47 like this. It's up to you. But now I can see that these 15 negatives are going to cancel out 15 of the 47 positives. Or you could say that there's more positives here than negatives, so the answer will be a positive. Then you just take the 47 positives and subtract the 15 negatives. And this difference will tell me how many positives remain after the subtraction. So 7 minus 5 is 2, 4 minus 1 is 3. I end up with positive 32, done. And there's our 3 objectives. And you could throw in there that we should be able to add and subtract with integers, but again, we've done that quite a bit in the past. That was all Unit 1 stuff, but now the fraction stuff that we reviewed in 3.0 is all Unit 2 stuff, which is it's not gonna go away in Unit 3. We're gonna need all 3 of these skills in Unit 3, and then also adding and subtracting in fractions as well.